Right, folks, it is my turn to try and introduce volcanoes to you. Just to give you a sense of where you are in the tectonics module, hopefully you should now have finished learning about all of the different types of plate margins and hotspots, got some revision notes on them, hopefully, ideally, watched the first episode of a series called Volcano Lies because it introduces volcanoes brilliantly to you. And actually, if you haven't watched it yet, I would probably stop this, go back and watch that one. I sent that to you on Tuesday the 23rd of June. So if you check your email from that day, you should find it hyperlinked there. This is my attempt at explaining volcanoes. You may well need to watch this in stages because there's quite a lot of content in this one. So you could do maybe a little bit over a couple of days or something. Right, we're going to start on page 22 of the module booklet. If you don't have page numbers because you've printed it off the internet, it's a page that says volcanicity at the top, and then there's a picture of a god. Okay, so we're going to start something that's not actually that important to the syllabus, but I just think it's really interesting. Bearing in mind, we've only sort of known about plate tectonics really since 1965, which is not, in the grand scheme of things, that long ago. How on earth would you have explained volcanoes if you didn't understand plate tectonics? Like, what on earth is a volcano if you didn't actually know what it is? So the name volcano comes from the god Vulcan. So the Romans had this god, and he was the god of fire. And you can see he's kind of melting metal in a furnace there. Well, do you kind of see what they were getting at? So they sort of thought that the god Vulcan was in charge of volcanoes and he used them to make things in his furnace. Other cultures, I'll come back to that, other cultures believed that volcanoes are the gateway to hell. And I have to say that image that you're looking at, you can kind of see where they get that idea, can't you? That this is just the entrance to hell. You can visit the original volcano, which is called Volcano. It's near Sicily. You get to Sicily and then you go to a group of islands called the Aeolian Islands, and they're all volcanic and they're brilliant, and you can go island hopping. So if you have a bit of spare time, once we're allowed to start travelling again, it is a really cool place to go and visit. Anyway, so that's where the name volcano comes from. It's all from the Roman god Vulcan. Ha-ha. The rest of page 22 is just some kind of facts and figures and information about volcanoes. It's quite interesting. For example, you can find out that at any given time there's probably about 20 volcanoes erupting. It also introduces you to this part of the world, which is really important for this module. You can call it the Ring of Fire, the Pacific Ring of Fire, the Pacific Ring, any sort of variation on that theme, but it's very, very important, as you can see on the screen, and it also has the statistic about volcanoes on page 22. This part of the world has 75% of the world's active volcanoes and 90% of the world's earthquakes. It's definitely a part of the world we need to know about for tectonics, and we will come back to it time and time again. I'm not going to open the hyperlinks on this slide. This PowerPoint is called Volcanoes. I've tried to be as straightforward as I possibly can. And if you're interested, those hyperlinks are to two different websites who monitor what's going on with the world's volcanoes, so you can find out where eruptions are happening and how much damage they're doing and all of that sort of thing. Okay, so page 22, just quite interesting for background information, really. But turn over the page. We need to start finding out why on earth volcanoes all behave differently. This is a very crude, simplified version, but essentially some volcanoes are like the one on the left, and some volcanoes are like the one on the right. They're both volcanoes, but they are clearly very, very different. And my job in this video is to do my best to explain why that is and what that means for lots of other things. And yeah, it gets complicated in places. As I say, you might need to do this video in stages, you might need to pause, you might need to rewind. That is not a problem. So before I go any further, I want to pick up on what it says in bold at the top of page 23 underneath the map. It says, the first important point to learn is that whilst molten rock is below the surface, it is called magma. Only once it has come out the top of a volcano does it become lava. So we are looking at lava because both of those images show volcanic eruptions. Magma is exactly the same thing, it's just underground. And we have two different names to just make sure we differentiate between where it is, okay? Magma is underground, it's not yet been erupted. Lava has been erupted, but they are both molten rock. Okay, so let's have a go. For those of you that want to kind of give your brains a little bit more of a chance to get ready, to gear up, those videos are gratuitous shots of erupting volcanoes, essentially. It just proves what I've been trying to tell you there in a much more exciting way. It will show you lots of different eruption styles from lots of different volcanoes. The reason I'm not showing them all is, firstly, it will make this video really, really long, and secondly, I have encountered a couple of copyright issues from playing other YouTube videos within my YouTube videos. So remember, the PowerPoint is called Volcanoes, and if you find that in OneDrive, you can then watch lots of lovely images of erupting volcanoes. Right, why on earth are you looking at custard? Good question. If you really, really hate custard, you can substitute these two images with that of gravy. Doesn't make any difference to me. What we want is a substance that can be quite runny and can be quite gloopy. I'm trying to think of a different word for gloopy. I just love the word gloopy. The correct word that we want is viscous. Okay, it's not a word that we use every day. It's not a word that you will be very familiar with. This is less viscous. This is more viscous. Why? Probably down to the amount of custard powder that you've put in. So this one doesn't have very much custard powder. This one has more. Or if you're doing the gravy version, this one's got less gravy powder. This has got more. Okay. If we're talking about volcanoes, which we are trying to, your custard powder or gravy powder is silica, okay? Mafic lava, which you can call basic lava if you'd rather, they're both equally acceptable. Basic or mafic lava has less silica in it, so it's less viscous. It flows, it can move quite easily. Silicic or felsic lava, some people call it acidic lava, which I know is confusing. There's just too many names for the same thing, but pick your favourite and go with it. So acidic, silicic, felsic. This has more silica in it, so it's more viscous and it doesn't really move very much. Right, hold that thought and let's see why that's important. Because the viscosity, so how runny or not your lava is, controls everything about your volcano. Everything. It explains the rest of it. Let's take shape. Now you've got this set of diagrams on page 25. If you don't have page numbers, turn over the page and you should see it. Notice that some volcanoes are pretty much flat, and then they get steeper and steeper and steeper. Now, calderas are confusing, and I'm going to explain them properly later on in this video. But for now, could you get a pen or a pencil and just kind of turn that into a stereotypical mountain volcano shape. So just add a nice big triangle on the top. Okay, and I promise I'll explain those to you in a minute. Flat, little bit steeper, 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 steeper. Why? Fischer volcanoes, which are pretty much flat, the lava hardly has any silica in it at all. So when the lava comes out, it's like this custard. It just spreads out very, very gently, flows, and you end up with a flat volcano. Each of these has a little bit more silica in it. The more silica you add, the more viscous your lava becomes, the thicker and gloopier it gets. It doesn't flow. So when it gets erupted from your volcano, it doesn't really travel very far. And hey presto, you get your steep-sided volcanoes. All right. For those of you that are less keen on diagrams, there is a text version of the same thing. And what I try to do is I try to keep the language as simple as I possibly can. So mafic lava has got less silica in it, less custard powder, less gravy powder, if you're going with that analogy, which means it's runnier or less viscous, which means you end up with a flat or very gently sloping volcano. Add more silica, it gets less runny, and you end up with a steeper sided volcano. Okay, so the amount of silica in your lava, firstly, dictates the shape. Secondly, it will dictate how it erupts. You have this diagram on page 27. If you don't have page numbers, turn another page and you will see it. You might want to number these because it's a bit confusing. This is 1, 2, 3, 4, 5, 6. Okay? 1, 2, 3, 4, 5, 6. Essentially, you're going from no ash cloud at all to a massive ash cloud, or notice, and this is not a coincidence, flat volcano, little bit steeper, 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 steeper. That is cause and effect, okay? It's all because of the lava. It's nothing to do with coincidence whatsoever. So let's take the Icelandic and Hawaiian ones. They're pretty much flat volcanoes. There is no ash cloud. The reason there is no ash cloud is because there is no explosion at all. The reason there isn't an explosion is because the magma doesn't have very much silica in it. It's less viscous, it's quite runny. And that means that when you get the gases, inevitable with any volcano, they're very gassy things. When you get the gases, they just bubble up through the mafic magma. The gas is constantly released, there's no build-up of pressure, you will never get an explosion. The more silica you add, the thicker, the less viscous your lava becomes. Now, the gas is still produced by your volcano, but the gas cannot escape. So it builds up and up and up and up until one day there is an almighty explosion, and then, hey presto, you have the ash cloud produced in the eruption. Okay, so the flat volcanoes are the mafic magma. They have flat or gently sloping sides because the lava spreads out very easily, and they don't have explosions because there's no build-up of pressure. If you would rather have that in text version, there you are. Please don't get too worried about what I mean by a pyroclastic flow at this point. If you've heard of them, great. If you haven't, they're coming soon. But just to go back a second. So this would be your mafic magma. Very runny, no build-up of pressure, nice pretty picture of lava. This one, very viscous lava, build-up of pressure over decades, hundreds of years, centuries, possibly even thousands of years it takes for the pressure to build until there is an explosion. And then, hey presto, you get a completely different end result. But the only reason you get the complete difference is because the lava type you started with. Okay. So you might want to pause there and think, I need my brain to have a little break. I'll come back another time. That's absolutely fine. Now, if you haven't had a chance to watch Volcano Live yet, the episode I sent on Tuesday, the 23rd of June, please, 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 at the very least, could you watch that section? They explain a couple of things really, really brilliantly. They explain the build-up of gas. I sort of did a pun then, didn't I, without even meaning to. They explain the build-up of gas in your silicic magma volcanoes. But they also pick up on another really interesting point. And I think because they've got a much higher budget than I have and some very specialist equipment, they explain it 10 times better. So please watch that, at least that sort of 10-minute section before you come back and restart this PowerPoint, okay? So the point that some people get stuck is they don't see this as lava. And I completely get why you don't, because this is what, as kids, we are brought up to think of as lava. It's orangey, yellowy, reddy, it flows, it looks really cool. That doesn't look like lava. Where does the ash come from? Now, hopefully you've watched the first episode of Volcano Live and seen the experiment. What happens is, at the exact moment that the volcano explodes, so the moment of the explosion, the lava is instantly solidified, okay? And it's solidified into a rock called pumice. And you may possibly have some pumice at home in your bathroom. It's used as an exfoliator for feet quite a lot. You might have a rock collection and have some pumice in the rock collection. If you haven't ever seen pumice, don't worry, when we're back at college, I will show you some. It's very, very light, but it is definitely a solid rock. So the moment the volcano explodes, you get pumice created. Literally a few milliseconds later, that pumice is blasted into tiny, tiny pieces by the force of the eruption, and that is where the ash comes from. It was lava, it is instantly solidified into pumice and then blasted into smithereens by the force of the eruption. Okay, and that's why you may have heard that ash is terrible for aeroplanes, for jet planes, and we will explain that in an upcoming video. The trouble with ash is if you have an open fire at home or you've ever been to a bonfire or anything like that, I think we often go around with this idea in our head that ash is quite soft and fluffy and, you know, disappears at the touch of a finger. This ash is tiny particles of solid rock. This is not soft and fluffy, it is super, super dangerous stuff. Okay, now if you haven't yet watched that 10-minute clip, you need to, because they explain it much, much better than I am able to. And here's the really cool bit, ladies and gents. So we've said that the lava type dictates everything about your volcano. It dictates the shape. It dictates how your volcano behaves. Does it produce lava? Does it produce ash? How big is the explosion? All of that's true. But here's the brilliant bit. Once you know the plate tectonic location of your volcano, you can predict its behaviour. Because mafic lava, so the less viscous runny stuff that gives you flat-sided volcanoes with no explosion, you will get that kind of volcano at divergent margins and hotspots. End of. Whereas the lava that has a lot more silicate in it, a lot more thickening agent, that's much more viscous, that produces steep-sided volcanoes with massive explosions, they're the ones you're going to find at a convergent margin. So once you've done all your mapping of your plate margins and hotspots, and then you've figured out where the volcanoes are, you know roughly how they're going to behave. How cool is that? I love that. So it comes back to those two diagrams. If you know the location, you can predict. This, I can tell you just from looking at that photograph, it's I think probably a Hawaiian volcano, just because I look at volcanoes too much, really. But I know it's a divergent margin or hotspot because I can see molten rock. This has got a pyroclastic flow, which is a very hot flow of ash. I'll talk to you more about those in another video, I promise. But I can see there's no molten lava. I know that must be at a convergent margin. And look at the steepness of the sides. I've got 2 giveaway clues that tell me that's a convergent margin volcano. Hey, that's brilliant, isn't it? Now, if I've kept you so far, I would definitely have a little break. Pause, come back another day, come back after a cup of tea, whatever. I'm just going to go into a little bit more detail. It's not any more complicated, I promise, but it is a little bit more detail. Right, so I just thought it would be useful to show you some real life photographs and maps of the different types of volcano. So this is a Fischer volcano, and a fissure is pretty much flat. It's actually like a massive crack in the ground that opens up. So that's the fissure, and you can see the molten lava coming out. And look how easily it flows and spreads out. So that's what a real life fissure volcano would look like. You get lots of those in Iceland, so they're quite common there. This is a shield volcano, which is named because of kind of a medieval shield. I don't have a medieval shield, so I've never tried this, but they say if you lie one flat on the ground, they kind of make the sort of shape that this volcano does. This is Hawaii. So it's got a little bit more silica in it than that one, but not very much at all. It is very, very gently sloping as a volcano. Composite, that is one of my favourite photos. I am not a photographer by any stretch of the imagination, but when the thing you're taking photographs of is that beautiful, it's quite easy to take a good photo. That's Etna, a bit more steep sides. That's not one of my photos, possibly unsurprisingly. Much steeper sides, ash cloud. See, you're becoming volcano detectives now, aren't you? Aha. Now, I promised I would explain these caldera things to you, and I really need to. Calderas are the most explosive eruptions. These are really dangerous, really devastating things. So, I asked you back earlier on in this video to complete the diagram on page 25 by adding some steep sides. This clearly is an artist's impression. It's not a very good one at that. But you can see here that we've got a steeply sided volcano, and here there's kind of nothing left. That's because, ladies and gents, the volcano that used to be here, its eruption was so explosive it destroyed itself. And I know that sounds bonkers, but that's how much pressure builds up, how explosive the eruption is, and therefore they just kind of blow themselves to smithereens. The most famous example is Krakatoa, and this erupted, as you can see, a long time ago, 1883. The dotted line is how big they think the volcano used to be before 1883, and then it destroyed itself. Anak Krakatoa, which I think means son of Krakatoa, is a new volcano that's erupting, but it's, as you can see, very much a baby. So that's how big the volcano used to be, and it doesn't exist anymore. The eruption was so explosive, it destroyed itself. In fact, the explosion of Krakatoa is the loudest sound in recorded history. Apparently, I wasn't around at the time, apparently everybody around the world heard it. Can you imagine that? That's just insane, isn't it? So it's about 13 times louder than a jet engine from 100 feet away, which is 30 metres. I mean, it's bonkers, this eruption. It caused a huge tsunami of over 30 metres and killed thousands of people. But of course, in 1883, we didn't have the technology or the communication to know very much about it. That's how explosive caldera eruptions are. All right, they're insane. Slightly closer to home, and actually a caldera that you might even be able to visit. This is Santorini in Greece. So this is the map version that you have on page 26. This is an aerial photo. So you can kind of imagine how big the volcano used to be, and you can see how effectively it managed to destroy itself. And it's very beautiful. It's a really popular tourist destination, very beautiful part of the world, but volcanic. So calderas are the most explosive. They used to be very steep-sided, but they are so explosive that they actually destroy themselves. Okay, just as a little aside, because you might be interested, you may have heard of the Bible story of the parting of the Red Sea. They actually think that that story might be based on the eruption of Santorini, because they think it would have caused such massive tsunami waves that potentially there were parts of the Mediterranean that didn't have any water on the seabed for the duration of that tsunami. So potentially Santorini is linked with a Bible story. And for the classicists out there, they think it was the eruption of Santorini and the tsunami created that destroyed the Minoan civilization. So potentially a few links to some of your other subjects. But my point is, caldera eruptions, they are steep-sided volcanoes, or should I say, they used to be, and they are definitely the most explosive. Eruption style, this is the point about whether they have a massive ash cloud or not. Notice that the vast majority of them are named after places. Well, we know that Iceland is a divergent margin and a hotspot, and the kind of eruptions you get there have mafic magma, flat-sided volcanoes, etc. There is only one odd one out, which is the Plinian eruption. Pliny was the person who described in writing the eruption of Vesuvius. So rather than being named as a Vesuvian eruption style or a Pompeian eruption style, it's named after him by Pliny. But Icelandic and Hawaiian would be divergent margins and or hotspots, and then the other four would all be at convergent margins. Okay. Now, again, this is a good pause point. If your head's hurting and you're thinking, oh my gosh, Nikki, this is quite complicated, pause before we do this bit. Have a little break. If you're good to go, brilliant. Now, I'm going to play with your brain a little bit here. Sorry. If magma rises at a divergent margin, cools and becomes oceanic crust, which is exactly what happens, and in a subduction zone, it's oceanic crust that gets subducted and melted and becomes volcanoes. If this magma produces mafic lava volcanoes, which are not explosive, less viscous, flat or gently sloping sides, yada yada, and it's oceanic crust that gets melted here, why on earth does melted oceanic crust give you a completely different volcanic eruption? Like, that doesn't make sense. It's made of the same stuff. What on earth has happened? Well, let me introduce you to this. There's nothing in your module booklet about this, because traditionally this is an area that students find quite hard, and we leave you to put notes in your own preferred format. Okay, so you might want to dig out a piece of paper or a revision card or whatever. Right, differentiation is where things begin to separate into different groups. So it doesn't only happen in magma, there are lots of forms of differentiation, but it definitely happens in magma. So the thing is, ladies and gents, here, the magma rises up, cools, becomes oceanic crust. There's no hanging around, there's no waiting, it's a direct process. So divergent margins and hotspots, the magma comes straight out, forms a volcano, job done. Here, It takes a long time for the oceanic crust to get hot enough to start to melt. It takes a long time for it to melt up through the crust, and then it hangs around in magma chambers for ages, potentially centuries or thousands of years. And that is where magmatic differentiation happens. It happens in these magma chambers. So I want to introduce you to the concept of melting point. Now, we are not talking about metal. This is purely as an example. Notice that all of these different metals melt at different temperatures. So zinc would melt at 419 degrees centigrade, but you would have to get the heat up to 3,399 degrees Celsius to melt tungsten. So metals melt at different temperatures. The same applies to minerals or rocks. Some of them will melt at quite low temperatures and some of them need it to be a lot hotter. So, in a magma chamber, you get this differentiation. Why? Well, partly it will be to do with weight or density. Some minerals will be quite heavy and they'll sink, and some will be quite light and they will rise up. We've talked about density on a couple of occasions before, but here is the more interesting point and the more relevant point. Melting points. If metals melt at different temperatures, they will also solidify at different temperatures. And if we're talking about magma, silica, which is our thickening agent, the thing that we add to make lava more viscous or less runny, silica is the last mineral to cool and crystallise. Which means the longer that your magma hangs around in a magma chamber, the more silica content it has, because the other rocks and minerals have solidified already. So they have gone to the edges of the magma chamber, they've cooled down, they've solidified, they're kind of out of the game, if you know what I mean. The longer the magma stays in the magma chamber, the greater the silica content. For the visual learners, here is a rough interpretation of a magma chamber. Geologists are likely to understand the labelling. Non-geologists, probably not so much. What we're trying to say though, look, is partly it's due to a weight or density issue, but it's partly the fact that silica is the last one to cool and crystallise. So the longer your magma hangs around in here, the more silica it gets. And the longer it hangs around, the more explosive your eruption, the steeper the sides are going to be, etc., etc. Magma does not hang around at divergent margins. It hangs around in magma chambers at convergent margins. So magmatic differentiation is why you get mafic or basic lava here, and you get silicic, acidic or felsic lava here. It's all thanks to a process called magmatic differentiation. Okay. So we have reached the end. You'll be overjoyed to know that was quite intense. It's really important, but you will probably need to break that down, rewatch, etc. When you think you are ready, the task on the left is a good idea. There's a table on page 24. For those of you that don't have page numbers, it says table of lava types and associated features. But most importantly, I've tried to do this video in good time for you to be able to send questions to Nick for his question and answer on Monday the 29th, because I have a feeling you might need to. Sorry, that's a bit intense, ladies and gents. I don't think it gets any harder now, to be honest. I think you've done the hard stuff and it's all fairly plain sailing from here on in, if that cheers you up at all.